So we're going to introduce simple linear regression, and I'm going to do it by starting out with the example we had when we did the one-way and two-way ANOVA. So we're back at the case where we have 4 different synthesis methods, 1, 2, 3, 4, and each of them produced 5 different yields. Not necessarily different, but we did the experiment 5 times. And we used the ANOVA to see if there were any significant difference between the mean yields of these methods. But let's imagine that instead of testing 4 different methods, we were testing 4 different pH levels. So we conducted maybe the same method at 4 different pH levels. And I'm not really a chemist, but let's just say pH 2, pH 3, pH 4, pH 1. So this changes the variable, we might call it the explanatory variable here. We changed it from being a categorical, a qualitative variable, into being a quantitative variable. Quantitative means that we can put a number on it. So it has a measurable size. And that enables us to do a more rich analysis of this data material. Now we can do a regression. And the first thing we always recommend that you do when you have some data material is to make a plot of it, if that's possible. So in order to do that, I'll just rearrange the data a little bit. So I'll take a copy of these data points here, move them down here, take a copy of this one, move it down here, this one, and this one. And then we just take a copy of these because they repeat themselves. Like that, and like that. And we can delete these over here. Right. So now we can make a scatter plot of these data here. So let's insert, and I'll choose the scatter plot here. And then I need to specify the data. So I'll choose data, select data here. And I'll add a data series. I don't care for any names, so I'll just go for the X values, which will be my independent values, the pH levels here. And insert. And then for the Y values, the dependent value, the dependent variable, like that, and OK to that, and we don't need to change anything. I don't care about labels or anything. So here we see that they are scattered somewhat, but there also seems to be a pattern in these data points here. So let's talk a little bit about what regression is. So if we didn't have any difference between the pH level, that is, the yield didn't depend on the pH levels, we might expect to see something like this. We get the same yield for every pH value. Of course, that would be a little bit strange if we got the very same value, because we expect there to be some random variation going on. But that's just one extreme case, you might say. Now, if there is a dependence between the yield and the pH value, we might expect something like, let's see, let's choose the red one here, like that. Okay, so now we have a clear dependence, a clear correlation, you might say, between the pH values and the yield values. But then there's also, this is not how the data distribute themselves. We saw that just a minute ago. What we actually saw was something like like this. Something like that. So the green one represents reality. That's what we observed. The red one would be if we had a complete correlation between the pH and the yield. So we need to think about, why is the dot here? Why is the green dot here, the green dot here? Why are they there? Well, part of the reason is the pH value, and part of the reason is some random variation. Okay, so the variation in Y has two contributions. There is something which is due to the variation in the X value. So some of the variation in Y we can explain by the pH value. But there's also something we could call random variation. It may not be that random at all, but it's due to factors that we don't know anything about. It could be the temperature or lots of other stuff. And since we don't know anything about those factors, we'll just call it random variation or unexplained. At least it's not explained by the pH level here. So the reason the green dot is here is because the model predicts, or the pH value predicts, that it should be here, but then there's some random variation which then causes it to be right here where it is. And the same thing goes for all these green dots. Let's say this one here. The pH level accounts for this variation away from the mean, and then there's some random variation which accounts for the rest. Okay. Another way to put this is that if I tell you that I did the experiment at pH 3.5, then you would be able to somewhat guess what the yield would be. You would probably guess for something in this area here, but you wouldn't be able to exactly predict the yield, and that's because of the random variation. So you'd be able to sort of narrow down the interval in which it would be most probable to find the yield, but you wouldn't be able to narrow it down to one specific yield. So that tells you that the variation in the yield is somewhat caused by the variation in pH, but not completely. And regression is all about finding out what proportion of the variation in Y is due to the variation in X and what proportion is not. And we'll try to do that in Excel. So having done the scatter plot in Excel, we can right click on a data point here and choose Insert Trend Line. And we'll choose it linear, and I'll put tick marks in these boxes so that I get the equation and the R squared value, like that. As you can see, there's a best fit linear regression here. It has this equation here, and there's an R squared value, which is called the coefficient of determination, which is 0.7. That means that 70% of the variation in the yield, in the Y value, is explained or determined by the variation in the X value and the pH values. 70% of the variation we can explain or predict using knowing the pH value. 30% we cannot. That's due to random variation. The way we determine this line here, where did this equation come from? I mean, it looks right. It seems to be a right model, but how exactly did we find this these numbers here? Well, that's Gauss's method of least squares. So here we have the data, and what Gauss found out was that the best line you can model these data points by is found by minimizing these vertical distances from the line. Not exactly straight lines these that I draw here, but you get the point. These lines here, or rather, not exactly the lines themselves, but the square of those distances should be minimized. So I'll try to draw, that's a tiny square there, and there's one here, and here's a square, and there's one, and here. The reason I draw these squares is that if you square this length here, you get an area which corresponds to this square here that I've drawn here. So what Gauss found out is that you get the best line by minimizing the sum of these areas here, these squares. That's why it's called the method of least squares. So if I change this line, the slope or the position of this line, I will change these squares areas here, and Gauss found a formula that would ensure that we got the minimum areas, the minimum sum of areas. And you can see it in the book. It's not that complicated, actually. So that gives us the equation, and we'll write it in this way. This obviously is the intercept, so that's this point up here, and this is the slope of the line, and we refer to them as regression coefficients.